Hi, the lecture today is about Newton's method for finding roots of an equation. Well, you have been solving equations for many years. You know how to solve certain equations. These are typically equations that fall in the category either linear equation like 2x minus 3 equal to 0, or perhaps one level higher, say quadratic equation x squared minus 5x minus 1 equal to 0. So you have the quadratic formula that you apply here. Here by simple manipulation you get roots, and a few special cases of trigonometric equations. Perhaps you know how to solve them, and that's about it. What if we face an equation that is more difficult? Suppose you want to solve x cubed plus 5x plus 1 equal to 0. Well, it turns out that there is a formula to solve this just the way you solve that one, but the formula is substantially more complicated than what you have encountered there. And what if your equation is even more complicated? Suppose you have like x to the power of 5 plus x to the power of 4 minus x cubed plus 7 equal to 0, something like that. Well, there is nothing, no formula that is going to guarantee to us that we can solve this in the same manner that we have been solving these type of equations. In fact, polynomials of degree 4 and above don't have any formulas associated with them the way quadratic formula had. And then even if somehow you manage this, there are plenty of other equations that are not easy to handle. Like suppose you want to solve cosine of x equal to x. That's not even a polynomial, and very soon we realize that it is rather a lucky situation that we actually could solve this kind of equations. More often than not, we don't have any theoretical way of getting an exact answer to the equations. What do we do in these cases? In fact, in a variety of cases, equations that we encounter, we go after approximation methods. So approximation methods they attempt to solve an equation, any of these, in a step-by-step fashion, going from a rough approximation to an improved approximation, in such a manner that if you continue doing that process, you eventually arrive at the exact answer, but after infinitely many steps. Among the approximation methods, the one that is famous is Newton's method, sometimes also referred to as Newton-Raphson Method. There are about half dozen competing methods of different efficiency ratings and different properties, and this is the one we're studying mainly because of one more application of differentiation. So the reason that this topic is in this section of calculus is that it has an application, it is one of the applications of differentiation. What I'm going to do is to first explain to you how the method works on a picture. Then we are going to go after a picture description, and then we are going to go take a look at the algorithm itself. Then we are going to have a simple example. You can find more complicated examples in the text. Then I'm going to end with a word of warning that what kind of things could go wrong all sort of pathological cases we might come across when we need to be aware of it and not to expect too much out of these methods. So let's take a quick look at this method from a pictorial point of view. Suppose I have a function y equal to f of x, so here's a nice function y equal to f of x. This function has an x-intercept. How do you find this x-intercept? Well, that's a point where y coordinate is 0. So the concept of x-intercept for a graph is the same as a root of an equation. This is same as root of f of x equal to 0. That has this property. Okay. Concept of approximations is we are starting from this my software is not behaving well again. We are starting with a guess of this root. Say we our first guess is somewhere around here. We are trying to guess the location of root and say this is what our guess is. Our objective in this approximation method is to improve our guess in a series of steps. So Newton method suggests the following. We go straight up to the function, graph of the function here. At this point we go ahead and draw a tangent line. If it is not our unlucky day, chances are quite high that we come closer to the actual root. So if you start at a reasonable guess on a reasonable function and draw the tangent line at that location, tangent line brings you to a better guess. So here's your next guess. We're going to call this guess number 1 x1. This is going to be our guess number, our second approximation to the root. Well, what do we do after we get to this better approximation? Just repeat the process again. So we go ahead to the point on the function, we go and find the tangent line here, draw the tangent line, find the third point. This is going to be our third approximation. Go again up, one more round, and so on. So this would have been like our x3, this would be our x4, and so on. We are going to get a sequence of numbers. The first one is supplied as a guess. That is going to provide the next one x2, that's going to create the next one x3, that's going to create the next one x4, and this sequence typically goes on infinitely many steps. It's just that as we go on, these numbers cluster next to each other and next to the actual root. Let's call the actual root here x star. That is the destination that we are after. Okay, that's a pictorial description of the Newton's method. Now we need to convert all of this into algebra so it can follow the algebra. Let's go ahead and draw this picture again. I have here my function. Say this is x1. We want to find out formula for x2. Our function here is y is equal to f of x. Well, what I really need to do is to find out how far to back up, to go from x1 to x2. So here is going to be my objective. Try to find this one. I go pay attention to this triangle that I have here. What do I know in this triangle? I know this height, that's f of x1, from here to here. That's f of x1. What else I know? Well, the slope of this line is same as the derivative of this function at this point. So here at this point, slope is f prime of that starting point x1. Is that enough for me to find out what this is? Obviously so. Let's see if what's the connection between the slope, this blue line, and this green line here. Let's go ahead and name these pieces. In definition of slope, you typically call this run. If you are starting from here, this could be playing the role of your run, and this is playing your role of your rise. This is just the rise. So what is the slope? Slope is a ratio of rise to run. So your slope here is f prime of x1. Your rise from here to here is f of x1. Your run is the quantity you're trying to find. How do you find the run? Just exchange the positions. The f of x1 over f prime of x1. Now what do I need to do? Start at x1, back up by as much as the run to get to x2. So x2 is x1. Now I have to back up by the run. What is the run? Just what we wrote up here, f of x1 over f prime of x1. That's it. That is Newton's formula. So that wasn't hard. We just a couple of steps, we arrived at Newton's iteration formula. So this is Newton's formula, or iteration, or algorithm if you wish to call it. Okay, by now we have done with the algorithm steps. Now let's go to a very simple example, as simple as we can make it without making it too trivial. Here's an example. Suppose I ask you solve x squared equals to, let's make it equal to 4. Find the positive root using Newton's algorithm. Starting at, so we give a guess for where we think this root is going to be. We hope that that guess is okay. x1 say is equal to 3. So what is our first step? Our first step is to go ahead and create our f of x. Sometimes you have to do simple manipulation to your function, to your equation, to make it appropriate for Newton's procedure. Here all you need to do is to bring everything to one side. That you have to do in every case. So I go ahead and define my function f of x to be x squared minus 4. The root of that is same as the root of this, and it is same as the x-intercept of, if I draw y is equal to x squared minus 4, the x-intercept of it is what I'm looking for. Of course, there are two of them. Depending on where you start, you're going to zoom in on one of these two. We are going to start on near this root, and we are hoping to catch that one. So Newton's algorithm says, here's Newton's algorithm. Says x2 is, you start at whatever you had and then you make a correction. So we are starting at x1 is equal to 3. Question is where x2 is going to be. It's better to go ahead and do the substitution of your functions here and simplify this for the particular equation you're working with. So I go ahead, rearrange my equation. I say x2 is equal to x1 minus f of x1 is going to be x1 squared minus 4 f prime of x1. That is 2x1. Derivative of this is just 2x. You could leave this like this. Sometimes it might pay to clean it up. I go ahead and clean it up. 2x1. This becomes 2x1 squared. Now I have to subtract this. So minus x1 squared plus 4. I get x1 squared plus 4 divided by 2x1. So to paraphrase, this is what we have. x2 became x1 squared plus 4 over 2x1. Simplified form of Newton's algorithm for this problem became this. Now what I'm going to do is take x1, plug it in this, and get x2. So I write x1 was equal to 3. x2, I just take 3 and plug it here. It becomes 3 squared plus 4 over 2 times 3. That is 13 over 6. This is one of the few places in this course that we are going to insist on decimal output because fractions are going to get out of hand. So here you convert it to decimal. Immediately question comes up, how many digits? My strong recommendation is to keep all the digits you see on your calculator. Well, that's too many to type or to work with it or to write on a piece of paper. And the solution is very simple. Just use the memory button of your calculator to keep this thing in memory so that you don't lose the digits. So by now we have obtained our x2. x2 is 2.16666, so on. Who is x3? x3 is going to be obtained from x2 same way x2 was obtained from x1. That is, say x3 is equal to x2 squared plus 4 over 2x2. So x3, I have to take this number 2.16, lots of 6's, square it, add 4 to it, divide by twice that number. Let me repeat my warning again. If you are entering these things by hand, typically you get lazy and not enter all the digits, or you make a mistake on that. If that mistake happens, things are not going to behave well. So once again, you keep these numbers in the memory. You learn how to handle the memory button. There's a memory button, there's a recall button typically. So you press the square after you press the recall, and that number gets to be squared. You go ahead and do that and find x3. What is x3 gonna be? Well, you go ahead and do this thing, and in this problem, if I have done it correctly, I'm gonna get 2.0064102, etc. You already see what's happening. We are getting closer to 2, and that was our hope, that we are getting to the exact solution. We go through this thing one more round. x4 is going to be calculated from x3, same way x3 was calculated from x2, and so on. That is, this is going to be x3 squared plus 4 over 2x3. That is, you get x4, you take this number 2.006 etc. plus square it, divide by 4, 2 times. Now, important thing is to get all these digits correctly, and once again, if you stop here, you are not going to get it correctly, and the process is going to slow down. So 2.00, I think 0, 0, 4 zeros, 1, 0, 2, and so on. You show all the digits you see on your calculator. You go through this thing one more round. Question is, how many rounds am I supposed to go through this? Well, it depends on what accuracy you want. How do you know you have arrived at certain accuracy? Suppose you want to 4 digits. If 4 digits of an answer from one step to the next step have stabilized, then you got it to that many digits correctly, and so on. Typically, Newton's method just takes 4 or 5 steps to become as accurate as your calculator can show. So if you reach at a stage that from step to the next step the result on your calculator doesn't change at all, it means you got it as accurately as you could. Like here, if you go ahead and do it one more round, in the next round, if I entered it correctly on my calculator, is going to have plenty of zeros, I guess 4, 6, probably as many as this, and then maybe they're going to show a 2. Well, typically your calculator doesn't go to so many digits. It stops somewhere around here, and if you take that number, enter it in your calculator and do it again, it just produces exact same answer again. Means you are not obtaining anything new as far as you can see, and that's a good place to stop. So once again, Newton's method typically converges to the answer as far as your calculator can show within 4 or 5 steps, and then you are all done. So you see, Newton's method is very powerful. Essentially, with just as many steps as you might have gone through a regular formula, you are getting your answer without memorizing much of a formula. Now we are going to go ahead and see what price do we pay for such a speed and such an efficiency. So next things that we are going to talk about is talked about the example. A word of warning: things are not as rosy as they seem. So next step is what can go wrong. In Newton's method. The formula itself shows what can go wrong. One of the main things that can go wrong here is quite obvious in the formula itself. The formula has a denominator. You have always received warning that don't divide by 0. Now here's a real warning. If this thing is close to 0, your x2 is going to be someplace that perhaps you wouldn't like. Let's go ahead and show this thing on picture. It's more understandable on a picture. Suppose you have a function, and the function kind of flat, where you're trying to find where you are trying to find the root. Suppose your x1 is chosen here, around where it is kind of flat. It's kind of flat means the derivative is kind of 0. If the derivative is kind of 0, it means that ratio is going to be a large number. Visually, if you draw the tangent line here, like our previous discussion, if you draw the tangent line, well, that tangent line could take a good time before it comes and hits the x-axis. Remember, the procedure was based on drawing tangent line, looking at the intersection, and that was supposed to be our x2. Let me take you back to the picture. Usual picture is that you draw the tangent line and you are getting closer to the root. Every now and then that doesn't happen. Like here, you draw the tangent line and x2 is way out there. All sorts of things could be happening all the way out there. Maybe the function is not defined, maybe a monster is living out there or something, so you don't know. Or it could be that you are right at the top here, and in that case f prime is exactly 0, tangent line is going to be horizontal, and there isn't even an intersection to find. So if f prime of some x, any of these x's, x1, x2, x3, any x is close to 0, so if that happens, the next number that we find is called the next iterate, will be far away. So what's bad about it? We are not getting close to the root, and all sorts of things could be happening over there. So that's one thing that could go wrong. How do we prevent it? Well, essentially there is no remedy other than making sure you are sufficiently close to the root. That might sound like begging the question, but there are ways of coming close to the root and then starting the process from there. The next thing that could go wrong is that your iterates might not behave as nicely as you want them to behave. Here's a picture that's going to show this peculiar behavior. Suppose your function has kind of inflection where it has its x-intercept. Now let's go ahead and draw something, see a funny situation is going to happen. You start at some location, you draw your tangent line, you come here, this is going to be your x2. At this point you draw your tangent line, lo and behold, you're back where you started. And if you do it again, you're just on the same loop all the time. You're not getting close. So that kind of unhappy coincidence could happen too. It's not quite common that the picture acts exactly like this. If you come close, the situation will get remedied, but it's good to be aware that this can happen as well. The third problem that could occur is, well, we kept advertising that Newton's method is very powerful and does an excellent job. In 4 or 5 steps you get the answer. In some cases actually it wouldn't. Here's an example of a situation that the speed is not going to be so good. If your root is one of these peculiar roots, your x-intercept is a peculiar x-intercept that the function doesn't cut through, but it just touches and goes back at that point, then the following thing is going to happen. Well, you start at some x, you draw the tangent line, and then repeat it again, and then you draw the tangent line. Sure enough, we do get close to the root, but if you go ahead and do an experiment with an actual function, such as say x squared itself, if you try to find the root, you'll see that it takes a lot more steps to come to the root than it did with the first example that we had. For example, in the first example we had x squared equal to 4 and tried to solve that. In 5 steps we got it. Here you could be going for 20 or 30 steps and perhaps you're struggling to get the root. So the problem we get here is a slow convergence. we are going to get to the root slowly. We get there, but very slowly. Here we are in a loop. We just go back and forth between same numbers. Here our iterates are getting lost. Essentially, we are going far away. Iterates are not behaving in a reasonable manner. Okay, make sure you go through the exercises, at least one of them. Find the root of one equation in this method. Using this method, you can, for example, take any of the problems in the text, or say this one or this one, and try to solve it with Newton method and compare with some other method you might have. Okay, that was a short lecture for today. I guess I'm going to stop this thing. Good luck and God bless.